Hi, in this video I'm going to show how to train a deep learning neural network in parallel using MATLAB parallelization features. MATLAB offers various parallelization features, many of them kicking automatically, but others you can use manually. And these are particularly useful when you want to try different training experiments. For example, you want to train a particular deep learning architecture with some hyperparameter combination, and then you want to do another experiment with different hyperparameters and a different network architecture. So those two experiments can be run in parallel, and that's what I'm going to show in this experiment. And I'm going to do it with the parfeval and features. The features work similarly to what you see for features in the standard C++ standard library. So basically you start the thread to run a particular function and basically get a feature. And this is non-blocking. So then once you get the feature and want to fetch its values, then it's going to block until the execution of the threads finish. So that's one option. And you can see here that I'm trying different experiments. I'm trying different architectures. I'm trying different training options with different hyperparameters. Okay, so that's one way. Another way that you can do it in a more primitive way is using parfeval. Parfor. Parfor is like a for loop, but it runs in parallel. So in this case, for example, I have a single hyperparameter, and basically I'm getting the mini batch size. I'm gonna use it for training options and then execute train network. So I'm basically trying for a set of experiments in here and running them in parallel. This is very primitive, but also limited. There are other options for training hyperparameters like experiment manager, in which you specify different hyperparameters and it's gonna run. And also you can specify different architectures here. This makes it more easy. So I'm going to include all of these references in the description of this video. In addition, there's this option as well, in which you can use this is called a single program multiple data, and it's another parallelization option, but you need to use some special methods. For example, a global operator, global plus, is like global addition. So there's some details in here. Might be more complicated. Okay, so let's start this example by doing open live script, and that'll take us to this screen. So let's get the digits data set. Basically, these are pictures of digits from 0 to 9, and the corresponding labels are the directory. And that's what we say here. The labels are the directory. And we're going to split it 80% for training, 10% for validation, 10% for test. We're going to use a data augmenter for a given range of translation, and we're going to do horizontal reflection. And then the augmenter, we're going to only use it for the training data and specify an image size of 28 by 28, and it's grayscale. And it's going to do resizing if necessary. Now we have our augmented training data store. So the training, I'm going to do the experiment in a couple different ways. I can actually, if you have multiple GPUs like this example shows, then you can run in multiple GPUs at the same time in parallel. It's going to be real powerful. But my machine, there's a method to know how many GPUs you have. The method is called a GPU device count, and this gives me 1. So what's going to happen is that I cannot use 2, so I'm going to change to 1, and by changing to 1, I'm going to create a parallel pool of 1, which is absorbed. What's going to happen is going to run serially in the computer. And I tried this both ways. I tried it with GPU and CPU, and in CPU, since I have multiple cores in my CPU, is truly able to run in parallel. But even like that, even with only one GPU, the GPU finished faster than the 4 CPUs running in parallel. Okay, so that's no surprise. That's why GPU is so popular. So what I'm gonna do is here I have the training options. I'm gonna put a breakpoint here so that you can see the execution. Let me put some breakpoints here. Okay, so for the training options, I'm gonna put environment. I'm gonna put CPU because we're gonna train. If you don't specify it, it will automatically go into GPU, and we don't want that. Okay, so let's put, since we have 4 experiments, I'm gonna use 4. This says GPU, but really is 4. Yeah, I had a pool already, so I have to delete the existing pool and run the command again. Okay, and now I'm gonna create a data queue. Data queue is basically to capture the data, and when you run things in parallel, it's not so easy to put a breakpoint and inspect things. So this data queue helps gathering the data from the training and being able to plot it. Okay, so let's get the options by executing this script. So from here we're gonna get 4 different architectures. The first architecture is gonna be a simple convolution rectified linear unit max pooling, and the second one has 3 of those combinations with an average pooling. And then option number 3 is gonna be the same as 1. Option number 4 is gonna be the same as 2. Now we have 4 training options. I understand that we're only varying 2 hyperparameters. One of them is the epochs. The first and the last are using 10 epochs, and the first is and the last are using 0.1 in learning rate. I don't know how different. I think the only difference between first and last is that you have different network architecture. So the middle ones have 15 epochs and a slower training rate. Okay, so let's finish this. And now we have our 4 options in here, 4 architectures and 4 training options. Okay, now let's prepare the plots, and that's gonna give us a handle. I'm not gonna go in details of this, just basically creating the graph where we're gonna plot the results. So that's gonna give us this. And now that handles are, we're gonna pass it to this. This actually, you can see it, this is a method. So what we're doing is basically to this method of data queue, we're gonna pass a callback, and the data queue is gonna give the data. This is gonna be the training data, and it's gonna update. It's gonna use that data with this method and put it into the plot that we just created here. Okay, so let's just pass the callback. It's not gonna execute now. Okay, so let's pre-allocate the features. We're gonna have 4 features. So okay, and now we're gonna run the features, and this parfeval is gonna run the train network, which is the most common method function to train neural networks. Is the easiest one, I think. And we're gonna pass the training data, and we're gonna execute this 4 times. So we're gonna pass each of the 4 architectures and options, and we're gonna launch a thread and capture the features. And you're gonna see that this is non-blocking. Yeah, so you see immediately that we can execute, and it's gonna start executing, but we're gonna hit the breakpoint of the update plots at some point. Yeah, so I'm gonna pause while this. Yeah, it was pretty fast. I didn't even pause. Okay. So what's going to happen is that we get the information, and you can see here that this is the training loss, validation loss, learning rate, because this can vary as well, accuracy, and all the information, and we're just going to add the points into a plot. That's all what we're going to do. And notice that debugging points are kind of problematic in parallel, and I cannot clear it. So I have to do db clear all to get rid of the breaking point, and F5, let it run. Okay, so you can see that it's really running in parallel. These trainings are gonna finish faster. And although, yeah, so I'm gonna pause until this finishes. Yeah, again, notice that when I launch the threads, I still can execute in here because they're non-blocking. But if I try to get the values, fetch the outputs, and put it, what I'm gonna fetch is a train information and the train networks. So let's fetch those values, and this is gonna be blocking. So this is gonna proceed once all the threads are finished. Okay, so I'm gonna pause this. Yeah, it looks like, yeah, they're still running all the same at the same time. Okay. Okay, the training finished. We got the train networks. We have 4 of them and the training information for each of them. And we can see clearly here that the fourth experiment, it gave us the best accuracy and the lowest loss. So now I'm not gonna go in details into this command. We're just gonna plot the results of the training information, and so we can see the same thing. The fourth experiment gave us the highest accuracy and the lowest error. So once we finished, we basically, after running those 4 experiments, we have 4 networks in here. So we pick up the 4, and that's gonna give us the layers, and the layers gonna give us the weights that of the training, and all we need to deploy that neural network. Okay, that's it for today. Thank you for watching.